Welcome back, everyone, for another deep dive. This time, we're going really deep, like atomic level deep, into something we see and use every single day. Metals.
Yeah, metals. I mean, where would we be without them? From like the cars we drive to the buildings we live and work in, they're everywhere, right?
Totally. But I gotta admit, I don't often stop and think about, what makes metal metal. What makes it so different from, say, the wood in my desk or the glass in my window.
Right. Like there's got to be something going on at a deeper level that gives metals those unique properties.
Exactly. So to uncover those hidden properties, we're cracking open a chemistry textbook that looks like it might be from India, judging by the examples it uses.
Cool. I always love seeing how different textbooks around the world approach these
Me
concepts.
too. So the goal of this deep dive, well, we're not turning you into chemists overnight, but we are going to explore the basic but super important properties of metals and nonmetals. And most importantly, we'll see how those properties play out in the real world.
Sounds good to me.
Awesome. So the textbook starts off simple with how we instinctively group materials, how they look, how they feel. It's like that gut feeling of, yep, that's metal.
Right. We use our senses, like that shiny surface, the metallic luster, or the feeling of a cool, solid object. And of course, the textbook talks about malleability and ductility, how metals can be shaped.
Oh, yeah, malleability. I remember that from high school, like
Mm.
how you can hammer gold into those crazy thin sheets.
Exactly. And gold is the ultimate example of malleability. You can stretch a single gram of gold into a wire that's 2 kilometers long.
Wait, 2 kilometers from just 1 gram? Seriously?
Seriously.
Wow, that's insane. I guess that explains why gold has always been so valuable.
Definitely. And it's also super ductile, meaning it can be drawn into thin wires. Think about all those tiny gold wires in electronics.
Right. But there's always an exception, isn't there? I mean, mercury's a metal, but it's a liquid at room temperature.
Oh, yeah, Mercury's the odd one out. Definitely breaks the mold there.
It does.
Hmm.
Okay, so looks and how you can shape them are important, but there's way more to metals, right? Remember those experiments back in school? Heating up wires and testing if they conduct electricity.
Ah, the good old days.
Right, so those experiments showed off another big thing about metals. They're awesome conductors of heat and electricity.
Yeah, that's why we use metal for electrical wiring. Got to get those electrons flowing.
Makes sense.
Yeah.
And to keep that electricity flowing where we want it, we need insulators, often made of nonmetals, right? Like, think about the plastic coating on wires.
Yeah, without that insulation, things could get pretty shocking.
No kidding. The textbook also says that silver and copper are the best heat conductors out there. So it makes sense why they're in so many electronics.
Makes sense. And have you ever thought about why a school bell is made of metal?
Hmm, not really, because it's loud.
That's part of it. Metals are sonorous, meaning they produce sound when you strike them.
Oh, interesting. So it's not just about function, it's about the effect too.
Exactly.
Okay, so we've been all about metals so far. What about their counterparts, the nonmetals? What makes them special?
Well, nonmetals are they're usually not as flashy as metals. They tend to be dull looking, not as strong, and definitely not good conductors. But hey, even nonmetals have their cool sides.
Right. The textbook even says that iodine, a nonmetal, is actually lustrous. Who knew?
It's true. And then you've got carbon, a nonmetal superstar that exists in some pretty wild forms, diamond and graphite.
Wait, hold on. Diamond and graphite, those are both just carbon.
Yep, pure carbon, but arranged in totally different ways, which is why their properties are so different. Diamond, with its strong bonds, is the heart of natural substance we know.
That's wild.
It is. And then there's graphite with its layered structure, which lets those electrons flow, making it a conductor, unlike most nonmetals.
So the same element can have totally opposite properties, just depending on how its atoms are arranged. Mind blown.
Mind blown is right.
Okay, so we've been talking about the looks, the feel, all the physical stuff. But things get way more interesting when we dive into chemical properties, don't they?
Yeah,
That's where we see how these materials really set themselves apart.
totally. It's all about how they react with other substances.
Exactly. And the textbook uses a simple experiment to show this burning magnesium, a metal, and sulfur, a nonmetal.
Oh, yeah, that's a classic.
And then they test what's left over, the solutions, with litmus paper.
Ah, the litmus test. Good times.
Right. So the litmus test tells you if something's acidic or basic.
Right. And it turns out that burning magnesium makes a basic solution, while burning sulfur makes an acidic one.
So burning them reveals a fundamental difference in how they interact with other elements.
Exactly. It all comes down to their chemical nature. Most metals, like magnesium, form basic oxides, while nonmetals, like sulfur, usually form acidic oxides.
Wow. That's a pretty big difference. And this seems like a good spot to take a break and dive deeper into how those chemical properties play out in even more fascinating ways in part 2. Welcome back to our deep dive into metals and nonmetals. Last time, we left off with that burning experiment with magnesium and sulfur, and it showed us how differently they react with oxygen.
Yeah, I mean, fire always makes things more exciting, right?
Right. But beyond the flames, it's really about those chemical reactions happening at the, atomic level.
Totally. It's not just about how something looks, it's about how it interacts with other elements, how it behaves.
Exactly. So let's see how they react with something else we encounter every day. Water.
Oh, yeah, water. Some metals go absolutely crazy when they touch water, like potassium and sodium. You got to store those guys under kerosene or they'll burst into flames.
Whoa, seriously. I think I've seen videos of that. Pretty wild stuff. Why are they so reactive?
It's all about their atomic structure, how easily they lose electrons. Potassium and sodium are kind of like eager beavers, ready to give up those electrons at a moment's notice.
Okay, so they're electron givers.
Yeah. And when they meet water, those electrons are like hot potatoes, quickly snatched up by water molecules, releasing tons of energy. Boom, fire.
So it's like an electron free-for-all, leading to an explosion of energy. I get it. But not all metals are that dramatic, right?
Definitely not. Aluminum, for instance, is pretty chill around water. It actually forms a protective oxide layer when exposed to air, preventing further reaction.
So it's got its own built-in shield, like a little suit of armor. The textbook mentions something called anodizing, where you intentionally make that oxide layer even thicker. I bet a lot of the aluminum stuff we use, like phones and laptops, are anodized.
Most likely. It makes them more durable, and you can even add color to it. Anodizing is a cool example of how we can tweak the properties of metals.
It is cool. Speaking of tweaking properties, the textbook mentions something called the reactivity series. What's that all about?
So, the reactivity series is like a ranking system for metals. It tells you how easily they react with other substances like acids or even that water we were just talking about.
Okay, so the most reactive metals are at the top of the charts, the superstars.
Exactly. And that helps us understand why some metals, like gold and silver, are found in their pure form in nature. They're not very reactive, so they just chill on their own.
The introverts of the metal world. Got it.
Mm-hmm.
What about those metals that are always ready to party, the reactive ones?
Those are the ones higher up on the reactivity series, like potassium, sodium, those guys. They're always looking to bond with other elements, forming all sorts of compounds. And because they're so reactive, we got to work a bit harder to get them in their pure form.
So this is where we get into metal extraction, right?
Mhm.
Getting those metals from their ores.
Exactly. And how we do that depends on where the metal sits on that reactivity series. For gold, sometimes you just got to physically separate it from the rock. But for most metals, it involves some clever chemistry.
Clever chemistry, huh?
What?
Give us an example.
Sure. Take zinc, for example. It's often found as zinc sulfide. So first, we roast the ore in air, turning that sulfide into zinc oxide.
So step 1, get rid of the sulfur.
Exactly. Then we heat the zinc oxide with carbon, a process called reduction. Basically, we're taking away the oxygen, leaving us with pure zinc.
So step 2, get rid of the oxygen. Clever indeed. But what about those super reactive metals at the top of the list? How do we wrangle those?
For those, we need the big guns electrolysis. It's like using electricity to force those metals out of their compounds.
Whoa, electricity. Sounds intense.
It is, but it works. It's like we're using electricity to pry those metals apart.
Wow, so we've got roasting, reduction, electrolysis, a whole toolbox for extracting metals. But even after all that, the journey isn't over, is it? The textbook talks about refining those metals to get them super pure. Why is that so important?
Well, even a tiny bit of impurity can mess with a metal's properties. Think about conductivity impurities can get in the way of those electrons flowing freely.
So for things like electronics, where conductivity is key, we need ultra-pure metals, right?
Right, and one way to achieve that is electrolytic refining. It's kind of like a metal spa treatment.
A spa treatment. Okay, I'm intrigued. Tell me more.
So picture this. You've got an impure copper slab, that's our anode, and a thin sheet of pure copper, our cathode. Both are hanging out in a copper ion solution.
Okay, so we're back to using electricity again.
Yep. We pass a current through the solution, and the copper ions from that impure slab start jumping ship, heading over to the pure copper sheet. The impurities either stay in the solution or settle down at the bottom.
So it's like we're selectively pulling out the good stuff, leaving the junk behind. Pretty neat.
It is, and it highlights how we can control those chemical reactions to get the properties we want.
Amazing. But even with the purest metals, there's always that pesky problem of corrosion, right? Rusty iron, tarnished silver, that green stuff on copper.
Yeah, corrosion is a constant battle. It's a natural process, but not always a welcome one. Metals react with their surroundings, leading to all sorts of changes.
The textbook focuses on the rusting of iron. It's like a classic science experiment, exposing iron nails to different conditions to see what makes them rust.
It's a simple experiment, but it shows something important. For rusting to happen, you need both air and water.
So it's not just moisture alone or just oxygen. It's the combo that's trouble.
Exactly. Rusting is essentially iron reacting with oxygen from the air and water to create that reddish-brown iron oxide we all know as rust.
It's amazing how those everyday things, air and water, can cause such dramatic changes.
It is. It's a reminder that chemistry is happening all around us, constantly shaping our world. But hey, we're not powerless against it. We've come up with all sorts of ways to fight back against corrosion.
Okay, tell us about those anti-corrosion strategies.
We can paint metals, creating a barrier, or use oils and greases to keep air and water away. Or we can even coat them with other metals that are more resistant to corrosion.
The textbook talks about galvanization where you coat iron with zinc.
Galvanization is awesome because zinc is more reactive than iron. So if the coating gets scratched, exposing the iron, the zinc steps up and corrodes first, sacrificing itself to protect the iron.
Whoa, so it's like the zinc takes one for the team. That's pretty cool.
It is. We're basically using our knowledge of reactivity to our advantage.
Clever. Speaking of using our knowledge, we've been talking a lot about pure metals. But what about alloys, where we mix things up?
Alloys are where things get really interesting. By combining different metals, or even metals and non-metals, we can create materials with totally new properties.
It's like we're playing mad scientist with metals. The textbook says that pure iron is actually pretty soft. But add a bit of carbon, and bam, you get steel, strong and hard.
Steel is a game changer for sure, and it doesn't stop there. Add nickel and chromium to the mix, and you get stainless steel, which is super resistant to corrosion.
So it's like the more ingredients we add, the more we can fine-tune the recipe for the perfect metal.
Exactly. It's like making a metal cocktail. The possibilities are endless. You've got brass, a mix of copper and zinc, used in instruments and decorations because of its golden color.
Oh yeah, I love the look of brass.
Me too. And then there's bronze, an alloy of copper and tin. It's tougher than pure copper and was used for tools and weapons way back in the day.
It's amazing how our understanding of metals and how they interact has led to such a wide variety of materials.
Totally. It's a story that spans thousands of years, from ancient techniques like the rust-resistant iron pillar of Delhi to those super high-tech alloys used in, like, spaceships.
Wow, that's a perfect spot to pause for now. Join us for the final part of our deep dive, where we'll explore those ancient techniques and modern marvels in more detail. And we're back for the final part of our deep dive into the amazing world of metals and nonmetals. We've talked about their properties, how we get them out of the earth, and even how we protect them from corrosion.
It's been a wild ride through chemistry.
It has. You know, last time you mentioned that iron pillar in Delhi, the one that's been standing for like over 1,600 years and barely has any rust. What's the secret behind its incredible longevity?
It's really a testament to the skill of those ancient metal workers. That pillar is made of iron that's super pure with hardly any phosphorus or sulfur, which, those impurities can really speed up rusting.
So even way back then, they had figured out a way to refine iron to make it last longer.
Yeah, they had a pretty good grasp of the basics. But there's more to it. The pillar's surface is covered with this thin layer of iron oxide, probably formed during its creation. And get this, that layer actually acts like a barrier, preventing more corrosion.
So it's like the pillar made its own shield. Talk about a self-defense mechanism.
Exactly. And it's worked for centuries. It just goes to show not all oxides are bad. Some of them can actually be pretty helpful in protecting against corrosion.
It's like turning a weakness into a strength. Okay, so we've talked about how adding carbon to iron makes steel stronger and harder. But the world of alloys goes way beyond steel.
Oh yeah, alloys are a whole universe of possibilities. Mixing and matching metals, sometimes even throwing in a non-metal, we can create materials with, like, custom-designed properties.
So it's all about getting the perfect recipe for a particular job. What about stainless steel? That's an alloy we see everywhere, and it's famous for its ability to resist rust. What makes it so special?
Stainless steel is a mix of iron, chromium, and nickel. And it's that chromium that really does the trick. When chromium meets air, it forms this invisible layer of chromium oxide on the surface.
An invisible shield. Cool.
Super cool. That chromium oxide layer is what gives stainless steel its superpower of resisting rust and stains. No wonder it's used in everything from kitchen sinks to, surgical tools.
Makes sense. But it sounds like the world of alloys is always evolving. What are some of those like cutting edge alloys that are pushing the boundaries?
Oh man, there is some seriously cool stuff out there. There are super alloys that can take insane temperatures and pressures, perfect for jet engines and things like that.
So those are the alloys helping us explore the skies and beyond. What else?
Then you've got shape memory alloys. They can be bent and twisted, but when you heat them up, they remember their original shape and snap back.
Right, shape memory. That sounds like something out of a sci-fi movie.
I know, right? It's crazy. But they're being used in all sorts of things now, from medical implants to robotics. The future is now.
It really is. This whole deep dive has been mind-blowing. We've gone from the basics of metals and nonmetals to like high-tech alloys that are changing the world.
It just shows you the power of chemistry. By understanding how things work at the atomic level, we can create some truly incredible material.
Absolutely. Well, I think it's time to wrap up this deep dive. Hopefully our listeners have a new appreciation for the metals all around them, from a simple nail to those super advanced alloys in our phones and computers.
I hope so too. It's amazing to think about how something as basic as the arrangement of atoms can lead to such a diversity of materials and properties.
It really is. Thanks for joining us on this incredible journey through the world of metals and nonmetals. Until next time, keep exploring and stay curious.